Today is a wonderful day. Birds are singing, the flowers are dancing, the Macarena or hula hoop or whatever the kids do these days, and the universe is not falling apart. Yes! Hello and welcome. And today we're going to be trying to understand something so monumental that the universe could not function as we know it without it. And to understand it, we're going to be looking at this. Such a magnificent specimen.
Have you ever looked at water and wondered, why do the water droplets stay together? Why does anything stay together, for that matter? Well, to answer that, we're going to be looking at intermolecular forces, which are pretty much exactly what they sound like. Forces that happen between and because of molecules that hold them together.
Officially, there are 4 intermolecular forces aside from traditional bonding, covalent, and ionic, such as in water. Although they are heavily influenced by these bonds. First off, let's establish that some atoms like electrons more than other atoms. For instance, chlorine really is desperate for that electron, and sodium is really desperate to give it away, which is why they work so well as a pair. It's also because it causes them to become ions. How much an atom attracts an electron is called electronegativity, and this is important because an atom with a greater electronegativity will have the electron more of the time in a bond. If it is great enough, it could become a polar bond, which means that one side is more negative than the other side, or it could be an ionic bond, where one side completely takes the electron and the other one just loses it. It's like, okay, bye! This is all well and good, polar, non-polar bonds, you already know this. But what does this have to do with intermolecular forces? Well, pretty much everything. Opposites attract, after all. That was the electron. Let's talk about some traditional bonding, starting with ionic. Positive and negative ions cling to each other like white dog hair on a black suit jacket. It's just... These come together to make crystal solids, which come in all shapes and sizes, like diamonds. No, not diamonds. What about molecules with covalent bonds? Well, these are no exception either. The polar molecules... The positive side of a polar molecule is attracted to the negative side of another polar molecule. So then they just kind of link together a little bit as they're passing by, and then just kind of float apart a little bit. But they're still attracted to each other in that way, but they're just kind of, I'll see you again someday. My impression of water, I could be an actor. This becomes more powerful when ions are dissolved in water. For instance...
Water is a polar molecule, as you can see right here by this magnificent drawing of the water frog. The positive side is where the hydrogens are, as they are just protons by this point, since the electronegativity of the oxygen holds on to the electrons more often. Water molecules arrange themselves around the ions, positive to negative, negative, positive, and surround them. To demonstrate this, we use distilled water to see how many drops can fit on top of a penny. As you can see, it builds a surface tension on top that is very... It took 54 drops of distilled water, and then with the help of the ions and the salt, it took 65. This is contrasted by the olive oil, which only took 29 drops. The polarity of an individual bond is determined by electronegativity, which increases diagonally across the periodic table, with fluorine being the highest and francium being the lowest. If the difference is big enough, it could become a polar bond, such as that of water. But the polarity of a bond itself is not the only thing that determines whether or not a molecule itself is polar or nonpolar. Molecular geometry has to do with this as well. For instance, carbon tetrafluoride has polar bonds, but the fluoride completely surrounds the carbon, making it nonpolar as a whole. For more information on this, please look at Shay's video by clicking on the velociraptor with a mullet right here! After this comes hydrogen bonds. Now, hydrogen bonds come from a molecule that has hydrogen in it, of course, that's why it's called hydrogen bond, but they also have to be connected to a water, a nitrogen, or a fluorine for it to be considered a hydrogen bond. They essentially have the same effect as a dipole-dipole bond, but much stronger. After this comes London dispersion, and to use the hydrogen as an example would be a really good choice. Now, London dispersion is when the electron of an atom is moving around. Now, essentially, that means that one side, wherever the electron is where it will be negative, and the other side will be more positive. This creates a partial positive and a partial negative. It's not as powerful as, say, a hydrogen bond, or any bond for that matter, but it is effective for things like noble gases.
So the more electrons there are, the greater the London dispersion force, until you know, it gets to be like one of those really big parties and everyone's like, whoa! As you can see, this all plays a part in salt water. You have the sodium ions floating around, you have the chlorine ions floating around, you got the polar water floating everywhere, just kind of going like, hey there. But then, you also have the London dispersion going everywhere, and and that is why the universe holds together. Thank you!
Walk, Ozzy, walk. Walk, Ozzy, walk.
Do it!